What's going on, everyone? Welcome back to the final lecture for the AI for Aspiring Researchers lecture series. In this lecture, we're going to be going over reinforcement learning. Now, you might already know what reinforcement learning is. Basically, it's it's an algorithm that is essentially like training a puppy, where whenever you adopt a new puppy, you train it by giving it treats whenever it does a certain trick. Similarly, with computers, or with reinforcement learning, whenever a computer completes a task which you feed it, you give it some sort of reward in the form of a number or something of the such. So what we're going to be doing is we're going to be applying reinforcement learning RL to the frozen lake problem. The frozen lake problem is essentially just a series of tiles, and you're told that you can step up, down, left, right, and you need to get from a start point to an end point, or goal. And so I've already run this program initially and the reason for that is reinforcement learning in general takes a lot of code, or a lot of understanding of the code, and in terms of running the code, it can take a while. So in order for this video not to surpass 40 minutes, it's best that we just kind of explain the code as it's already written. And so you'll see here, this is kind of how the game is structured, where you have a start path and a goal, or a start tile and a goal tile, and your objective, or the computer's objective, is to go from this S to G. And the point is, you can't hit any of these H blocks, because those are considered holes in, say, the floor. And then these F blocks are places which the computer can stand on. And so the idea, or the objective, once again, is to go from S to G without stepping on these H blocks. Okay, so let's jump right into it. So the first few lines of code are obviously our libraries, and you can already notice NumPy and the pyplot are probably the more common ones, and we've already seen those before. But there's also import random, that's fairly self-explanatory, obviously just kind of generating a random number, but this library is a new one. Now, what Gym is it's basically just a library that has all the environments from OpenAI. So what OpenAI is, it's basically just a provider of all these environments that you can train your reinforcement models on to see how well they work. And so you might have heard of, say, computer models beating Atari games. Atari games, you can kind of pull them from this Gym library. You can create these Atari games using this Gym library, and it'll return an Atari environment, is what we call it. Right, and then there's different types of games. So there's a car racing game, or in our case, a frozen lake problem game. So I encourage you, after this video, go and try out those different games and see which ones would fit you best, or not fit you best necessarily, but which ones you like or enjoy the most. Okay, so the first real bit of code is going to be our hyperparameters. So the first hyperparameter is the number of episodes, which we set as 30,000. These episodes are just the number of times which we actually train, or number of times this reinforcement model plays the game. You can think of it, right? So if we had this grid right here, how many times is our reinforcement model going to play this one singular game, right? Or you can think of, say, Atari Breakout. How many times does it play Atari Breakout? Okay. Next is going to be the learning rate, and we've already seen this before with neural networks. It's a similar model here, only, I guess, used a little differently, and you'll see exactly how, because instead of neural networks, we're going to be dealing with Q tables for our reinforcement model, but learning rate applies just the same way. Similarly, you have a hyperparameter called discount. Now, discount is just another hyperparameter for this Q learning, and we'll see how that applies to an equation later on as well. Next one is epsilon max, which we set as 0.9. Epsilon max, what that just means, it's a trade-off of exploration versus exploitation, right? So whenever a random value is generated above epsilon max, we want to actually get a predicted value, right? But whenever it's below, we're just going to output some random action. That's the exploration phase, whereas the prior one was the exploitation phase. And decay, what that means is, over time, we know that our Q table, which is essentially this huge table of values that determines how we're going to predict an action, our Q table is going to become much stronger in terms of the way it predicts. It's going to become much more better in terms of predictions. And so we want to explore less and less, and we want to exploit that Q table more and more as we run more and more episodes. And so this decay, what that's doing is it's decreasing this epsilon value so that over time we're exploiting more of that Q table as opposed to exploring these random actions that might give us something better. But it's unlikely the longer we run it. Okay, so the next thing is also env is equal to gym.make and then frozen lake v-v0. So this is just pulling from this gym library the environment for frozen lake. And what an environment includes is these different methods that are able to return the state of an environment. So that means what is the layout of the game board at that exact moment, or the amount of reward a computer gets for completing a certain action, these types of things. And you'll see that right down here, env.step, and we'll explain that in just a second. Okay, so lines 13 and 14, we have size underscore actions and size underscore OS, which stands for observation space. So what these are just the total number of actions and observation space, or observations that you can just see from this game, right? So actions is the total number of things that you can do at a certain point, right? So your player can either move, or the computer can move either up, down, left, or right, and that would be the action space. So this would be 4. Whereas this observation space is the number of observations really that you can have. And so in this case, in the frozen lake case, this is these are discrete values, which means that there are certain X number of actions that you can take, or a certain number of observations or kind of states, I suppose, that you can see in the game. Whereas in a lot of cases nowadays, we see that these action spaces and observation spaces are not discrete. They're actually continuous, because a lot of what you can do you can't just necessarily do discrete things. You can't do an X number of things. You can do an infinite number of things, and for that you have continuous spaces. And if you approach a problem that has a continuous space, how you would go about doing that is by first converting your continuous space into different segments, and then kind of treating it as a discrete space. But for now, because this is very preliminary and very beginner, we're going to be dealing with these in discrete spaces. Okay, so the next thing is we're going to create our Q table, which is just going to say np0s, size OS, size action. So it's very simple. All we're doing is we're creating a Q table with a bunch of 0 values. And this Q table is going to be changed over time. So right now you can kind of think of this Q table as, well, I don't know what's going on, but in the future I'm going to be able to change the values in my table so that each value corresponds to a certain action given a certain state. And then as those values change, the better and better predictions you get. Now, rewards is just a way to keep track of the past rewards for our past episodes, and we're going to be plotting all our rewards so you can see how exactly the reinforcement learning model learns over time and how it gets better. Increments, we said, is 1,000. This is something that you don't have to do, but it's something that's nice and probably recommended. And the reason for that is whenever we're actually rendering, render just means showing the actual image or kind of state in picture format, or in our case text format, of our game. This increments, what it's doing is, rather than for every single episode printing out, it's just doing it for every 1,000th episode, right? Because what would happen is if we didn't have increments and we rendered it every single time, that would mean that we're rendering 30,000 images, which is a lot and would take a significant number of time. And so instead what we're doing is we're just rendering the every 1,000th one. So we're only rendering a total of 30 images. And so you can see over time how those things work. Okay, so the next thing that we are going to do is actually have our for loop. So what this is going to do is it's going to run through all the episodes and kind of iterate through every single episode. Now for each episode, we're going to have to reset the state. And the reason we have to reset the state every single time is because let's say that in our first run, we do hit the goal. But if we don't reset the state, that player will just remain at the goal at the start of the second episode as well. And then whenever the second episode starts and you ask it, is it done? Yes, it's already done because it's already at the goal. But in reality, that's not what we're expecting. That's not what should be happening. What should be happening is that the player should restart at the start space every single time in order to find its final path. And so that's why we hit environment or env.reset. Then we're going to say total is equal to 0. Now total is just a way to keep track of our rewards, nothing fancy there. Total rewards, right? And then done is equal to false. So like state, we don't want to say that whenever it reaches the goal, done will be set to true. But whenever we restart, we have to set done equal to false, since we don't want to imply to our computer that we're already done with the entire game and you've completed what you needed to complete. That's not true. Okay, and you can kind of see that in this while not done, right? Because if we had done over here and it printed out true, or it saved as true, then when we came back, and if we say assuming didn't have this value, so if we say commented that value or line out and we didn't have that, then it would say while not true, which would be while false, and it would never actually run anything new. So we need to set this done is equal to true. Okay, so inside here, this is where the actual Q table or Q learning comes into play. And so the first thing that we're going to do is use that epsilon max value to our advantage for our exploration exploitation trade-off. So this if-else statement, what it's basically saying is that if this some random number is greater than our epsilon value, then we're going to pull from this Q matrix. And this that's just a more fancy way of saying we're going to exploit, or we're going to take the maximum value in this Q matrix and apply the action that corresponds to that index. Right, so if say we had a table right here, or this imaginary table, you can kind of think of it, and each of these values in this table have some different value, right, between 0 and 1. Now what this is doing, argmax is doing, is it's saying, okay, what is the maximum value in that entire table? Now the column, I believe, should correspond to the action number. So if say that action, or that largest number, is in column 1, then it would mean that we're going to be taking action 1. Okay, now else we're going to say action is equal to env.actionspace.sample. This is just another way of randomly selecting an action. And that's what this epsilon is doing, right? Because if it's ever greater than epsilon, we're going to exploit. If it's not, we're going to explore. Okay. Next thing that we're going to do or say is new state, comma, reward, comma, done, comma, underscore is equal to env.step action. Now this underscore is just info, but we don't really use it, so you can just put info or underscore or anything you want there. But the step thing, what it's doing is that it's actually changing the environment, right? Because what we're doing is we're taking an action, and said action changes the environment. So we have to create a step in our environment. And this step will return something back, because whenever we apply an action, we come to a new state. That's what it's returning here. And because of said action, we get a certain amount of reward. If we took a good action, we get a high reward. If we get a bad action, or if we do a bad action, we get a lower reward. And this done just means, have we reached the goal, or are we done with the game in the sense that we jumped into a hole accidentally, or the computer didn't or failed to complete the task in a required amount of time. Right, and so total plus equals reward. This is just adding our total reward to this total value over here, which we'll be using later. And then what we're also going to say, now this is the main thing. This line right here looks very daunting, but it is the main idea of a Q table. So what it's saying is that Q matrix state action. So in the Q matrix, that value that we took as the max, or the value that we took as that we chose, is going to equal to this. Now, what I would suggest is don't try to learn what this exactly is, because not even I know precisely how they derive this. It's a very complicated thing in general. So if you want, feel free to just copy paste that line or change whatever you want to change for it, because it is fairly daunting to just look out. But basically what it's doing in essence is just, it's updating the Q table. This is the update. So we're setting our new Q table value to whatever this value is. And this is where that hyperparameter of discount comes into play and the learning rate, and you can tweak those hyperparameters as well. Okay, so then you also have state is equal to new state. Now, what this is doing is that whenever we take that step, we got back a new state, but we need to set this new state as our current state so that whenever we run through the loop again, our computer will evaluate at whatever new step it came to rather than just staying at the old step and evaluating at that same exact point constantly. If we didn't take a new state, then we would just be stuck at the same point forever. Right, so that's why we have to constantly iterate through our states and then finally see whether we're getting to what we wanted to get in the bottom. Okay, now we're going to also say if e percentage sign increments is equal to 0, print total reward, and then env.render. So what this is doing is it's just saying for every 1,000, right, e mod increments for whenever the episode number iteration we're on, mod 1,000 is equal to 0, if it's a multiple of 1,000, then we're going to print our total reward for that episode, and we're going to render the environment. So I'll show you what that does exactly right here. So this is our first kind of 1,000th number. So this is a 1,000th episode right here, this first little block of words right here. So we're printing out our total reward, which is just 0. And the reason it's 0 is because it didn't achieve the goal. Right? Because whenever the reward is 0, that means that we didn't get to where we wanted to get. However, if the reward was 1, and I'll try seeing it here, right? So if the reward is 1, that means that we achieved the goal. The computer got to the final point where it had to get to. But if it's 0, that means it either got stuck in a hole or it just wasn't able to find a final path to get to the final goal. And so what render is doing is it's just printing out based on the environment library or the environment that we imported, in our case the frozen lake environment. It's just rendering whatever state it's in. So this you can see is the tile. So this is where we started, this was the goal, and this is where we ended, whatever is highlighted. And as you can see, it's kind of difficult. Right? What that says is an H, which means that you landed on a hole and you fell down, so the computer failed to achieve its task. Okay, now this next thing is saying epsilon max times equals decay. Now what this means is that over time, we want to exploit the Q table more as opposed to exploring randomly. And so decaying is going to decay that epsilon value, so that every time you run a new episode, you're decreasing the chance that you're going to explore another action as opposed to actually exploiting or choosing or predicting a proper action from the Q table. Okay, now finally what we're going to say is sums is equal to 0, average rewards is equal to a open brackets, and this is just going to actually print out, this code right here is going to append to this average rewards the average reward seen thus far. Now, that makes, I think seeing the code and analyzing the code makes a lot more sense, and also seeing the graph makes more sense afterwards. So I'll show you that right now, actually. Let's see, right at the end. Okay, so as you can see here, this is the final graph for our reinforcement learning algorithm. So what this is showing is that over time, our algorithm is actually increasing in terms of the number or average reward that it's getting, right? Because the max reward is 1 and the worst reward is just 0. And so towards the end of our training, or towards the end of our training, the reinforcement algorithm, we're landing values that are around 0.6, which is actually fairly good, which means that more than 60% of the time, our reinforcement algorithm is able and capable of predicting how to get from the start position to the goal position. And so it's fairly accurate in terms of reinforcement models, but obviously it can be made better by tweaking, say, hyperparameters or kind of applying new things to it. And right now we're using a Q table, which is actually pretty preliminary. However, nowadays a lot of people use deep QNets. And so if you want to go ahead and check that out, I would definitely recommend that, because deep QNets typically, they're neural networks in essence, right? So they're using neural networks to be able to predict a Q table, if that makes any sense. Hopefully I'll be kind of updating with a video on exactly how deep QNets work as opposed to just Q tables in general, and you'll be getting a more of a better understanding of deep QNets then. But for now, I hope this makes sense. Um, Once again, just in summary, what we're doing here is we're rendering this image or every 1000th time. And so this is where the computer ended at the 1000th episode. And then as you can see, as I scroll down, more and more ends or more and more episodes, you see the computer achieving the goal that it was meant to achieve. And so for that reason, in the graph, we see this sudden rise over here in terms of how well our computer program is performing. But for now, I'm going to leave you off on that. I hope this is a lot to take in, and what I would recommend you do is try following along with this code and try to see if you can apply this to a couple of things. One, try to apply it to different environments. Right now I'm using the frozen lake, which has both an action space and an observation space that are discrete. However, many of the environments in the OpenAI gym are going to have continuous spaces. And so try to figure out a way, if you can, to make them discrete and then apply this whole algorithm to them. And the next thing that I would kind of recommend you guys do is see how can you make your own environment, right? Because right now with a lot of the open AI, it's typically games that they're playing, or very specific or niche reinforcement learning. I guess, yeah, games would be the best description of them. But let's say, for example, and I know a lot of people do this, is reinforcement, say, for stocks. Now, if you can create an environment for that mimics the stock market, or that mimics a stock and has different values or attributes of a stock, and you can create or different states of a stock or rewards based on how well a computer performs on a certain, say, daily return. These are all different things that you can go ahead and think about and try to figure out a way to actually create a state. And so those are the two things that I'd like to leave you off on. But thank you guys so much. This will probably end the majority part of this AI for Aspiring Researchers series. I've really enjoyed making these videos, and I hope you've enjoyed listening to them as well. And happy coding!